Marco! All right, picking up where we left off, we were talking about how to find the derivative of y with respect to x. You individually take the derivatives of y and x with respect to t, and then just take the quotient of those two. So let's take a look at that quotient right there. Let's say, like, one of the things that we often have to find on those free response questions are vertical tangent lines and horizontal tangent lines. So if this is our formula for finding the slope of a parametric set of equations, how would you find horizontal tangent lines? Yeah, okay, so how does the slope equal 0 from that?
The x derivative is 0. Right.
No, yes, the y derivative is 0, but the x can't also be 0. So otherwise you get 0 over 0, and then you'd have to use L'Hopital's rule to see what actually happens. So how would you find vertical tangent lines? Yes, the derivative of x is 0, but y cannot be 0. Or again, you'd have to use L'Hopital's rule. So definitely write something down for each one of those. So you don't often have to find the whole entire derivative or whole entire slope dy dx. You could just see what the derivative of y with respect to t is if you only had to find horizontals, say. But you still have to compare it with the bottom to make sure it's not 0. It would be just like them to throw one of those in there. Just like them. All right, so then let's go back to that problem that we found, the kind of sideways parabola. We found its derivative, but it was after we had eliminated the perimeter. So let's try it with this definition here. So right here, let's find the derivative of y with respect to x. For some reason, there's a little box that's hanging here. It's like they're playing hangman. I'm going to say that's what it is. Here, let me finish this off. Yeah, hangman. All right, a letter. A? Okay. A. All right. Anyway, enough fooling around. Enough fooling around. Okay. So to find dy dx, I know that that's supposed to be dy dt over dx dt. So what is the derivative of y with respect to t over here? This is 1. That's pretty easy. And then what is the derivative of x with respect to t? 2t minus 2. So here's the derivative of y with respect to x. And now notice that this derivative is a function of t now. This does not exactly match up with the one that we just got, right? Because that one had y's in it. Are they the same? How could you make it the same? That's correct. So remember, we have right up here that t is equal to y minus 1. So if we substitute 1 over 2 times y minus 1 minus 2, 2y minus 2 gives us 2y minus 4, which I think is what we had before, right? So apparently the formula works. If the proof wasn't enough, you know how it is. Okay. So let's say then that we have to find all the horizontal and vertical tangent lines. Well, for a visual inspection, we could very easily get it, but we wouldn't necessarily have this graph here. So we're just kind of applying the same kind of things to this exercise. So horizontal, we'll start with that one first. So to get horizontal, I need dy dt. So dy dt is just simply equal to 1, and that's never equal to 0, which means what? Right, and we can take a look at that graph. Yeah, there's definitely no horizontal tangent lines there. All right, so So now let's do vertical over here. Switch some colors. So now we want dx dt, which I think we already found, right? 2t minus 2, set that equal to 0. So t's got to be equal to 1. Now, this just says find all horizontal and vertical tangent lines. This just gives me a t value. What am I supposed to do after that?
Plug it back into the X and Y.
Right, now this is a vertical line, right? So it's possible that they ask you for the points at which you have vertical or horizontal tangent lines rather than the equations for it. That seems more common. So let's say that we find the points where this happens. So I need to plug it back into the parametric equation so we can find the x and the y coordinates. So back up here, if we were to stick in 1 for our, stop moving around, for our t, 1 squared minus 2 times 1 gives us -1. 1 plus 1. So do I have a vertical tangent line at -1 comma 2 on this graph? It'd be right here, right? -1 comma 2. Does that look like this would be a vertical tangent line? Looks like it to me. Okay. All right. Let's see what else is going on. Already found that. Already found that. Ooh. Find the intervals over which it's concave up. Second derivative. Okay, so we're not going to start with the parametric version of it again, because we're going to get the wrong answer for some reason. So we'll go back to the first derivative that we had before in terms of y, I think. So dy dx was equal to 1 over, reminds me, what was it, 2y minus 4? Okay. All right, if I'm going to take the derivative of that, what would you suggest that we do?
Move it.
Yeah, move it up. Yeah, that's what I would do. -1. So are you one of those that avoids the quotient rule at all costs? Turns it into...
It ended up being really tedious in some cases.
Right, okay, so we got second derivative is equal to, leapfrog that thing down, -2y minus 4 to the -2 power. Is that all? Yeah, times the derivative of the interior. What's the derivative of the interior?
2 dy dx.
Yes. And remember, this always happens with the implicit differentiation. Whoops, I put t. That you have to back substitute. So let's clean this thing up and do some back substitution. We'll have a -2 dy dx up top. And on the bottom, 2y minus 4, all of that squared. I want to take away that dy dx that's up top there. And substitute what in its place?
The 1 over 2y minus 4.
And I already have 2y minus 4 squared on the bottom, which means that I can take the one that's on the top, cram it down, let it join up with its friend. And so our second derivative should be equal to a -2 over
2y minus 4 cubed.
Yes, 2y minus 4 cubed. All right, we found our second derivative. What did we want for this? We wanted concave up. So concave up happens when greater than 0. So usually what we do, of course, is we find critical numbers, right? So my critical number, I'm not going to get anything from the top, but I can get something from the bottom. Critical number there, 2y minus 4 is equal to 0, 2y is equal to 4, so y is equal to 2. And then, you know, we usually set up like a little interval. Do you remember what the smallest y value was from our graph?
0.
I don't think so. No, y value, yeah, yeah, 1. And then I think it goes to 5. So it's from 1 to 5 is what our intervals are going to be. So interval, we're going from 1 to 2. 2 is our critical, or I guess super critical. And from 2 to 5. And notice that what we're doing is we're picking y values to go in here. So I'm going to put a y. Let's pick a y value here in this first interval. In between 1 and 2?
Yeah,
You,
1.5.
okay, all right. You want 3 halves?
Yeah.
All right, how about in between 2 and 5?
Gotta keep it uniform.
Yes, okay, let's keep it consistent. Now, where do those go? They're going to go in the second derivative. Right, that's the only place it can go. All right, so whenever I take 3 halves of 2, that's going to make that 3 minus 4. That makes this thing negative down on the bottom. Negative divided by negative makes it positive. And that means our curve, what do they call this curve? C? C, yeah, that's a cup. So I'm going to guess the other one's down. Let's see, if we put in 5 halves, that'll be a 5 minus 4, which makes it a positive 1. Negative divided by positive makes this negative, and it's a CD. So we're concave up over the interval from 1 to 2 for the y's. For the y's. So at 1 less than y, which is less than 2. Let's look at that graph for that. Does that make sense? Y value of 1. Here's the y value of 2. This is the tiny little portion where it's concave up right there. Yeah. Yeah, I agree with you. Totally hold water. Okay. Yeah, there's all of that stuff. There's all that stuff. So let's see the animation here play out for the second derivative. Let's see if we can do the second derivative. Is this that? No, this is what we were just looking at. That's what we just did. Okay, here we go. Second derivative. Let's see if we do it the same way that we did with the first derivative. I mean, it makes sense. That's what everybody would think, is that you just take the second derivative of x with respect to t and the second derivative of y with respect to t and just divide them, right? That's what we did with the first derivative. Let's see. So here's your first derivative. Its second derivative of x with respect to t would just be just 2. All right, and then all right, then on the right, what's the first derivative of y with respect to t? And its second derivative? 0. And then if you take the quotient of those two things, it means the second derivative is always 0, but it wasn't. What kind of graph has a second derivative of 0? Yes, it's line. Yes, it's a linear equation. Right. So yeah, that didn't work. So yeah, there's something else that's happening. Let's see. Oh. We're hoping that mathematicians can figure it out by the time we take the BC calculus exam. Yeah. The Y's broken. All right. All right, so we're going to think of the first derivative as a function of x. So I'm going to say, like, our dy dx is a function of x on its own. So I'm going to say f prime of x, but x is in itself a function of time. So I'm going to take the x out and replace it with the g of t that's right here. Okay, and now I'm going to take the derivative with respect to time on both sides of this. So on the left-hand side, it stays d dt dy dx. That means the derivative of y with respect to x, you're taking that derivative with respect to time. Okay? Yeah. I know, because it's the, I got to find the second derivative. Oh. Right, so we're saying that the derivative is a function of x. So this is that first derivative, and we're taking its derivative. You might be looking at the second. Are you looking on the first one or the second one?
No, I'm looking on the slide. Like that, on the screen. No, it's dy equals f of x. dy over dx.
Oh, you're right. No, this one, you're right. That should have been this one. It was always there. I don't know what you're talking about. Look at that. You see it?
Yeah, what are you talking about?
Peyton,
There's an apostrophe right after that.
does your copy not have it or something? I don't know. All right, what color are we on?
No, it's not recorded now.
Okay, anyway, so the derivative with respect to t, we're taking that of the thing that is a composite function, so we'll have to use the chain rule on it. So it'll be f double prime composed with g of t times the derivative of the interior, and the derivative of the interior is g prime of t. All right, let's change this stuff to Leibniz notation. So in the place of f double prime of t, I'm going to put the second derivative of y with respect to x. d2y dx2. And what do I put in the place of g prime of t? dx dt. And then we would want to solve this thing for the second derivative. We solve this thing for this by dividing the dx dt to the other side. And then this gives us our formula for the second derivative. So it is the derivative with respect to t of the derivative of y with respect to x over the derivative of x with respect to t.
Simple.
Right? Yeah, it's obvious.
Look how small it is.
Was this just a proof again?
Yeah.
Honestly,
Yeah, so it was to understand where this derivative formula is going to come from. So it doesn't come out of left field, because if I showed this to you, just the formula, it'd be like, why do we divide it by dx dt again?
in other words, the real analysis.
Yeah, it's the real analysis part of it. That's correct. Yeah. All right, so here's all of that thing played out. Wait. Shh. Okay. All right. And then there is your derivative, second derivative of x, of y with respect to x. Here, let me put both of them here together for you. And so look at what the pattern is. So now the pattern is pretty much established. Whether you look at the second derivative, look at what the third derivative is. You will never have to take the third derivative on the AP Calculus exam. It's just to show you what the pattern is. Yeah, so this year. Let's see, there weren't enough problems this year. Let's put a third derivative of a parametric set of equations.
You know what? Let's put the fourth first. Let's just put all of it on there.
Yeah.
Yeah, I don't know.
On Tuesday of not this Tuesday, but a week from Tuesday. Uh-huh. Uh-oh. Carter's starting to panic. Do you see it?
That's a big.
Okay.
Yeah.
Sorry about
Well, some of it is going to be, you just have to sit down and practice it, and then the pieces will hopefully fall into place. Okay. All right. So let's rework the other problem and show that we can, in terms of t, still be able to find the second derivative. So here is when we found the derivative of y with respect to x, just parametrically. All right. So now if I want to find this second derivative, d2y dx2, the recipe is you take the derivative with respect to t of the first derivative, dy dx, and then make sure you divide it by dx dt. All right, so the derivative of y with respect to t, I have to take this thing's derivative right there. So to do that, of course, I'll probably rewrite that as 2t minus 2 to the -1 power. All right, then. Now, we're taking it with respect to t, so t is the independent variable here, so there's no implicit differentiation. Okay, it is negative 2t minus 2 to the -2 power times 2. All over. And now the dx dt, it's what that derivative was, which was 2t minus 2, right? And then just clean this thing up. -2 up top. Bring these things down to meet their friends. 2t minus 2 to the 3rd power.
It's wrong too. There's another way.
Now notice that this one, of course, is a function of t. When we did it, we had a function of y, right? Is it possible to get it where is it? It's right
Y does equal
there.
t plus 1.
That's correct. So you could substitute it in and show that it's exactly the same. Now let's say, for example, we still had to do the concavity thing. Add a page. So let's say that we had our second derivative and now it's in terms of t, and I still need to find out where it's concave up. 3, 2, 1, 8, and 2. You do it exactly the same way. It's just that now it's in terms of t's instead of y's. You still find your supercritical. 2t minus 2 is equal to 0, so t is equal to 1. And now I need to split up not my y variables, I need to split up my t variables. So t started at what and went to what?
8 plus 37.
No, that was a different one. I think this one went up to, was it 5 or was it 4?
That was 5.
Let's say, yeah, it was 5 because it was 4 plus 1 to get that y value 5 that you shouted out. Do you remember?
Yeah, I got it.
Yeah. Okay, so it's 4. So this thing goes from 0 to 4. That's what we have to split up with our intervals. Apparently, I'm using red exclusively now.
Yes, there's 5. 0 to 4.
Yeah, no, I'm just,
It's 5.
The y value is 5, but
Yeah.
the t value is 4. All done?
Yeah.
Okay. Yeah, put it with the rest of that stuff, yeah. All right, so we're going to have the interval from 0 to 1, and then from 1 to 4. T values are what we're going to select this time. Like what? 1/2. Okay, and this is going to go into our second derivative there. So if I plug in notice, of course, the top is always negative, so really we just care about the bottom here. If I stick in 1/2, that makes that a 1. I subtract 2, it's negative. Cube, it's still negative. Negative divided by negative is positive. And so C is cup. If I stick in 3/2, that becomes a 3 minus a 2 is a positive 1, and then cube that thing, it's a negative divided by positive, which makes it negative, and it's CD. Now, so we did the same exact test, except now it's in terms of the t values instead of the y values. So I would say here that it's concave up on 0 is less than t, which is less than 1. Ta-da! Luckily, that's pretty much all you have to do with parametric equations. That's a big fat lie.
Oh. Should have practiced it.
Okay. Well, it's pretty much all the calculus that you've learned, almost, just so it's parametrically.
Well, we have an entire day on it.
Yeah, we still have integrals with parametric.
Intervals of parametrics. I'll pass.
How much
Yeah, we do have to find arc length. That's it. So you're not finding area or anything like that. Polar, yes, but not for parametric. Okay.
How much of these tests is it?
What did we saw? We saw the other day was what, about 15 to 17%?
Yeah.
Are you joking? What? Or we're just now learning it now.
We're just now.
Yeah. I mean, in any calculus book, it's always the last section.
I mean, it makes sense why, I
It's the
guess.
big finisher.
Yes, that's right.
Here is a 17 to
It's finishing like,
18%.
wow,
Yeah.
this is kind of easy.
Okay. So our curve D is defined parametrically as t equals t, or x equals t squared, y is equal to t cubed minus 3t, and this is set up to be an f or q. We want to show that it has two tangent lines at 3, 0, two tangent lines at one point,
Parametric is 11 to 12%.
11 to 12. Did they change it since the last time you showed it? Okay.
Oh,
Can we try? That's not hard.
You wanna?
Yeah.
Okay, so let me pause the video then and let you guys try.
I don't think we have a choice. Can't see. Yeah.